So you will have seen how we can make quick one-off devices or two-dimensional planar structures using electron beam lithography. There is now a new tool, though, anticipated by Richard Feynman in his lecture that we discussed in Chapter 1, that will shape material pretty arbitrarily. Anything that you can chip away, you can make in a focused ion beam milling machine. Now, a focused ion beam is just what Feynman suggested. It's an electron microscope at which the source is held at a very high positive potential instead of a very high negative potential for a source of electrons. And in particular, the source is a source of ions, particularly gallium ions. The reason being that they are readily melted into a liquid source, and liquid sources are readily ionized by the formation of a sharp cone of liquid called a Taylor cone in a high electric field. So by using lenses which tend to be electrostatic rather than magnetic in a focused ion beam, because of the difference in the charge to mass ratio of an ion versus an electron, one can bring a beam down to a sharp focal point on a sample, and because of the increased momentum of ions in the ion beam compared with electrons in the electron beam, atoms will be knocked out of the surface of the material being bombarded. In fact, these are very versatile systems and can come equipped with lines for reactive gases that either by writing with electrons or ions can let you deposit metal or carbon films, for example. And in the instrument that we have, they actually have two beams. So a sample sits like this, and then in one direction an ion beam comes down and mills the sample. So gallium ions, and then in another direction an electron microscope images the area being milled at the same time that it's milled. So the source of gallium is shown here. It's a little filament on which is suspended a gallium source in this container here, which is both heated and ionized to form the beam of gallium ions. And B shows some of the things that happen when these ions impinge on a silicon surface. They generate, of course, silicon atoms they liberate from the surface by imparting momentum to them. They also, of course, bounce off the surface themselves and can generate secondary electrons. They can also implant in the material. So one drawback of focused ion beam milling of materials is that a pure silicon sample, for example, will become contaminated with gallium ions implanted into it, and that will affect its electronic properties. So for that reason, focused ion beam milling is best used for applications where one mechanically wants to shave a sample away. Here are some examples of structures made by focused ion beam mills. You can see on the left here the slogan of a British university, its seal and the name of the university, and the scale bar at the bottom, notice, is 3 microns long. So you can see structure on the nanometer scale etched quite quickly, and I'll give you an example of this in just a minute, etched quite quickly in a focused ion beam instrument. So the example on the left is sort of fun, but here is some serious application in the semiconductor industry. The focused ion beam, in addition to being able to make three-dimensional structures, can also cut through materials with exquisite precision. And so what one is looking at here is the gate of a field effect transistor on a chip. So the plane of the chip lies back into the photograph this way, and here the device has been milled right through using a focused ion beam and then imaged, and so you can clearly see the failure of the gate dielectric on this transistor. So their operation and programming is a lot like an electron beam lithography material. One feeds the instrument a bitmap file of the structure that one wants etched, and then the ion beam is scanned over the surface and turned on and off appropriately. With a dual beam focused ion beam, though, one can see this operation in action and look at nanostructures as they are etched. So in the movie I'm about to show you, you'll see ASU for Arizona State University being etched in the surface of a piece of silicon. At the end of the movie, the silicon is tilted and brought into a better perspective for imaging by the electron microscope column on the machine. You'll notice that electron microscope imaging while the ion beam is etching is a little noisy, but nonetheless you can see the nanostructure being formed as it is scanned. So let's take a look at the movie. So you see already within a few seconds the surface has been etched away enough to produce quite a striking image. We continue to etch. And now the sample is going to be tilted around and imaged at higher resolution by the electron microscope. And there you see it. Direct top-down fabrication in action with a view that looks almost as though one was using a macroscopic milling machine.